All right, let's look at the questions here. The first one. So the first question here is actually about to find the general solution for this differential equation. So these are some typical second order differential equation. Okay. So follow the steps. The first step is of course the auxiliary equation, which we actually get the coefficients from the left hand side, and we're actually like solving like this quadratic equation and get the roots. So those roots, okay, we just have to sort of like recall the form. So these are the roots. That gives us this complementary solution. So whenever we want to write these solution here, just be careful of the variables. So because this is like a x in terms of t. So when we actually write the complementary solution here, it should be something that is like a x in terms of the t as well. So this is something that we should just like recall. Okay, what is the form? So we have got the complementary already. So we need to actually look at the particular solution. So what we have for the particular solution here is that we have got this is the xp, okay, we make it to be like a times e power at. So because we have got like this e power at term here, okay, so we just assign the coefficient to that. And after that, we will actually have the x prime, so we will actually differentiate it, okay, and also the x double prime, we differentiate it another time. So what we have later, okay, is that okay, we will actually have to substitute all these x double prime into the d squared x dt squared, and then substitute the dx dt and also the x itself, so that we can actually compare with the right hand side there in order for us to solve for the constant a there. So the constant a here is a negative one, so it actually gives us like this xp is a negative e power at. So this is finally the general solution for this differential equation here would be this form, which is like x is in this form. Okay, so that's for our first question. Okay, in the second question, okay, so this is about the reduction formula. This is to integrate 1 plus 3x power n with e power negative 3x, where n is an integer. So first we need to show that, okay, 3in is equal to like this expression here. So basically for this kind of the expression, we see we have got a product of like different functions here. And we just have to have a look at the reduction formula here. So we have something which is like an in minus 1. So of course, this is something that is involving the by parts. So as we actually do the by parts here, that is like, okay, we will let the u to be 1 plus 3x power n. The reason is that as we actually differentiate it, so we will actually get like the power n minus 1. Okay, so of course, when we differentiate it, we also need to differentiate like inside the bracket there, so we get a 3. So overall, we get a 3n multiplied by this. So we have got the dv, okay, it's e power negative 3x, so we can actually find the v very easily here. So that we can actually sub in the values into the, so this is a uv, and then this is like a minus integral of the v du, so it has got a negative here, right? So it will actually become a positive here. The evaluation part, just sum in the values of like a 1 and a 0 to evaluate from there. So you need to be careful that because most of the time, right, we will actually assume that when the x is a 0, then we'll just assume that the whole term is a 0, because it's so easy to actually make that kind of the assumption, or it's so natural for us to actually assume that whenever we see something like an x inside there. But in fact, this is not, yeah? So we have to really sum in and check. It will actually give us a certain value, which is like a 1 over 3 here. Okay, so not always a 0 when the x is a 0 here. Just be careful about that. So that would be the evaluation part for the first two terms here. And then for the last term that we actually see at the right hand side there, it's something nice. Once we actually try to tidy up the stuff here, right? So basically the 1 over 3 and the 3 will actually cancel off nicely. It will only give us this integral here. So basically this integral is the same as what we have in the earlier integral there. So the difference here is just like the n and n minus 1. Okay, so with that, we will just have like, that is our I n minus 1. So we just have to tidy that up a little bit. Okay, basically it's to multiply the whole equation there with a 3. So that is the reduction formula that we can actually get for this part A here. So with that, right, there should be some follow-up questions sometimes. Okay, yeah, so is to find the exact value of the I2. So we need to see what is the first value of the I that we need to find. Okay, so basically, okay, they tells us that this IN is having like the N is an integer here. So it means that N could be any value in this case here. Okay, so if N could be any value, so I mean like here we could actually like find any IN that we want from scratch. Okay, from scratch. So of course the easiest IN that we could find is actually like the I0. Okay, because N could be anything here. It's not limited to a certain value. So the easiest that we could actually start with is to find the IN from scratch. We need a starting value first, then only we can proceed. So I0 will actually like make this term power 0. So everything will just reduce to like e power negative 3x. So the result is very nice. Okay, after we actually do the integration then. So afterward, it is to actually like apply, okay, the reduction formula again and again only. So once we have got the first value, we just have to keep substituting, okay, into what we actually have here. So everything will actually just give us, what do they want? Okay, they want an I2. So with the I0, we find the I1, and with the I1, we just have to sub in the value again, and then we can actually like work until we get the I2 there. So the integrals here are actually in terms of like a constant and also like all the e power negative 3 there. Okay, so that's for our second question about the reduction. So if we look at the following question there, okay, so this is a matrix A, which is given by this matrix here. So we need to find the eigenvalues of the A. So the eigenvalues of the A here is we need to actually find from using, okay, the determinant of the lambda I minus A is equals to 0, some standard procedure. So make it lambda I minus A, and we equate the determinant of it to 0. Here you could choose to expand by using any row or column. But certainly, the easiest one for us to actually expand is to use the second row. Okay, is to use the second row here. So also remember the sign, okay, this sign here. So for the lambda minus 6, it should actually have like a positive sign. And then when we actually use this lambda minus 6 to actually expand, right, we are just looking at this thing only. So the remaining would be this thing here. So it's very easy, okay? So we just have to like expand the determinant inside there. It gives us some kind of like a quadratic. So the lambda minus 6, we will just leave it like that because later on we want to solve for the lambda. So it's better for us to use a factorized form first. So with this, we can actually like tidy up and we will get like a quadratic, which we could factorize it very easily. So once we actually factorize it, okay, we can actually solve all the values for the eigenvalues here. Okay, usual stuff that we do all the time. Okay. So in the following part, so is to use the characteristic equation of A to find the A inverse. So this is actually not like we are using the adjoint method to find the A inverse as usual. This is we must use the characteristic equation. So from the characteristic equation, we will somehow have the expressions earlier. So just feel free to use any form of it, but of course, I think we will actually use this one to actually do the second part there. Okay, so to get the characteristic equation, we need to like expand it first. So from the factorized form just now, we expand it. So with this equation, which is in terms of the lambda, we can change it to the polynomial, which is like in terms of the A. So basically, it's like we sub in the A into this polynomial here. So once we sub in the A into the polynomial here, we get all the powers of the A there, including, so don't forget to actually like include the identity to the constant there. Okay. So from this equation, we want to get A inverse. So in order for us to actually get the A inverse, we could just reduce like all the powers by 1. Or in another word, we multiply the whole equation with an A inverse. So it actually gives us something that has like an A inverse there. Okay, so in order to actually find the A inverse here, it is actually depending on this. Okay, so we have to we need to have like a A square, we need to have the A and also like the I here. So in a calculation there, we could actually try to calculate the A squared first. Okay, if you think that this is very troublesome, use a calculator to help you to check the answer. Okay, basically when they check the working, right, they don't expect us to show something like this already, right? We don't need to show this already because it's quite a lot. It's a 3 by 3, so they don't expect us to actually show this. They just want to see the answer here. Basically, you could just use your calculator to check your answer. Okay, so we have got the A square already. So I do it separately is because if you actually do it one shot, it might be very confusing or it might be very long. You might get mistake from that. So I actually take out the A square and do it separately. Then only after that I submit everything. So this is 1/144 negative A square 16a and also the 36 identity. So from here, then we will actually have got like this result. Okay, so how like this is the A inverse, right? Because we have the original A, right? So we could use the calculator to check this answer as well. So we can check whether we got the this matrix of the A inverse correct or not. Okay, so we could always use the calculator to do the checking. Okay. So if we move on to look at the next question then. Okay, so this is a question about the area of the rectangles. So, okay, what we have for these y is equals to ln x for the curve here is to consider the sum of the areas of this rectangle, show that we have got the ln n factorial is greater than this expression here. So we need to actually like look at two things here. One is, okay, we have got the area under the curve that we want to compare. So the area of the curve that we want to compare is from 1 to n. Okay, so we need to integrate the ln x from 1 to n. So integrating ln x, we know that we are going to use the by parts. So when we use the by part, we get the x ln x minus x. I guess in the mark scheme, they don't even bother like how do we actually get this. They just want to see, okay, the answer is like this. Okay, so sum in the values for the n and the 1 there. So this is the result that we get. So we have got the area under the curve already. So we are looking at the rectangles. So what are the heights of the rectangles here? So the width is 1, okay? So we just look at the heights of the rectangles there. So the heights of the rectangle, the first height is when we have got the x equals to 2. The last height is when we have got the x is equals to n. So as we actually add up all the rectangles, the area of the rectangles there, that would be like ln 2 until we add until the ln n there, in which, okay, we actually know about the ln, right? We can actually like multiply all the terms there, 2, 3, 4 until the n. So this is basically the expression for the n factorial there. So that's how we actually prove that we have got like an n ln of the n factorial, and just restate what is the thing they're actually comparing. Okay, the rectangles is actually higher than the area under the curve. So that's for our part A. So in our second part, so we need to find an upper bound for the ln of the n factorial. So it is like, what do we actually found like in this case here is that, okay, we have got for the ln n factorial, it's greater than. So this is actually the lower bound. The lower bound of the ln n factorial. It means that the ln n factorial is something like this. So we just found the lower bound. Lower bound here means this is the rectangles, right? This is the area under the curve. So previously we have the area under the curve is less than the rectangles. Now, when we want to find the upper bound, is we need to make sure that the area under the curve is actually larger than the rectangles. Okay, so the usual way that I would actually consider is that I will push all the rectangles to the right by 1 unit here. Okay, so after I actually push the rectangles, so these are the rectangles that we're actually getting. Okay, so these are the rectangles that I'm actually getting from there. So whereby we actually have got the area under the curve, okay, that we want to compare now is, you can see it's from 2 to the n plus 1 already. So it's from here to here when we compare the area under the curve. Okay, so we just need to find out what is the area under the curve from there. And we have already performed this integration earlier. So just substitute the new values inside there. So this is actually what we get. Okay, as for the ln of the n factorial, because we are actually using the same set of the rectangles, so we don't I mean, we don't really have to actually show it already. But of course, in this question here, right, you can see the space that they give us is actually quite a lot. So if you could reproduce the diagram and then you can actually sketch the rectangles, so it's easier for us to actually see the things there. Okay, you could reproduce the diagram here. Just sketch it and sketch what are the rectangles that we're actually using, and we can actually have a very nice presentation of our answer here. Okay. So, okay, this is okay. This is a curve that has a parametric equation for the t is in between half and 2. So we need to find the exact length for the c. Length, okay, the arc length is we need to find the dx dt and the dy dt, square them, add them together, and put them in a square root. Okay, so we will have to see like what are the things that we could actually achieve from there. So when we actually try to square the two things there, right? And then this is what we actually have so far. So t squared plus a 2 plus a 1 plus a t squared. They are different expression that we might actually end up with, okay, when they actually gives us different types of the parametric equations here. But for this one, it is the form that, okay, is in fact the perfect square. So we can actually like make it into something that is like squared. So it will be cancelled off with the square root there. So that is why we're actually getting like t plus a 1 over t. Okay. So after that, it's not difficult for us to actually do the integration. So the arc length, it is just like the square root of the dx dt squared plus the dy dt squared. So we already have the expression simplified. It is just the usual t plus 1 over t. So we can actually integrate it very easily. So we get half t squared. Integrating a ln 1 over t gives us a ln t. So just sum in the values from there. And of course, the things after that is just a bit of the simplifying, okay, and tidy up. So this would be the exact value of the arc length that we will get from there. Okay, so this example is similar to what we have done in the exercise before. Okay. So now they actually ask us to find the d square y dx square. So to find the d square y dx square here, that is, we need to first find the dy dx. So dy dx is very easy to find. So dy dt over dx dt. So we will actually get some expression which looks like this, not so friendly, okay? So we have to tidy up a little bit so that we get such a nice expression, okay? Rather than just leaving it like the second line here, it's not good. So we want to actually have like dy dx is a nice expression. So with that, right, okay, what we need to do is that we need to, okay, do the second derivative. So the second derivative, there are two steps involved. One is from the dy dx, we differentiate it with respect to that variable. So here is t, we just differentiate as usual with respect to t here. So here we have to use the quotient rule. So we have to use the quotient rule here. So at last, okay, at last, when we want to find the second derivative, remember we have got an extra step there. So other than differentiating the dy dx itself, we need to divide, okay? Always remember to divide by the dx dt. Okay, so this is what we have for the derivative of the dy dx, and to divide by the dx dt there. So after that, we just need to tidy up a little bit. So this would be the expression that we will actually get for the d squared by dx squared there. Okay, so parametric equation, the second derivative is always like one more step, so you just need to remember that formula. Okay. Okay, so this question, so starting from the definition of a clan and a shack, okay, in terms of the exponentials, okay, so we need to prove, we have got this expression here. So that is actually what we have, like the clan, okay, we need to actually use the sine over cos for the definition, and then we square that. So at last, right, what it actually gives us is that it is just having a single shack term. So from here, the first line that we see here, we can actually combine the terms. Okay, so it is good that we actually combine the terms, because in the numerator, lots of things we actually can cancel out. We will only have got like a constant 4 here, which the constant 4, right, we can actually move it down there to become a half. Okay, sorry, I actually forgot to square this. So we can actually move it to the bottom there, it become like a half square. So it is within the bracket here. So half e theta plus an e power negative theta, the whole thing squared there. So this is actually giving us like a 1 over cos square, which is like a sec square there. Okay, so when we use the definition to do, make sure we are trying to like, so it's not like from here, then we reach like the conclusion, which is like the sec square. So it's better for us to show one more step and say that, okay, this is how we actually get the sec from there, or the cos square from there. Okay, for the first part then. So, okay, it's some differentiation question again for this part B here. So they tell us that, okay, we have got this, fan y is a cos x plus a 1 over 4 pi. So by differentiating this equation, show that we have got the dy dx is given by this expression here. Okay, so it's actually very interesting for this. In fact, okay, we can differentiate the relationship here. So tan and also the cos. Differentiating the cos, not really an issue. We get a negative sign. For the tan, right, okay, we are actually getting like a sec square. Okay, and because we are differentiating with respect to x, but here is a y here. So we need to multiply by a dy dx. So at last, right, there is actually no y that is actually involved in the expression here. So we need to try to express everything back in terms of the x. So that is to apply the idea where we have got like the sec square is actually like a 1 minus tan square. So why do we actually change it to the 1 minus tan square is because we know that the tan y is actually a cos. Okay, so the tan squared here becomes like a cos square. So 1 minus cos square is again our sine square. So the sine can be cancelled off, and we just move one of the sine over there, and then we just rearrange. So it should be actually giving us this expression here. So it's a negative cosecant of this x plus 1 over 4 pi. Okay, so that's for the second part. So in the following part there, so hence, okay, find the first three terms of the Maclaurin series for this arctan of the cos of the x plus 1 over 4 pi in this form. So if, I mean, like they want us to find for the Maclaurin series for this, okay? So the y here is actually like the arctan of the cos of the x plus 1 over 4 pi. So it is the same like we want to find the Maclaurin series for the y here. Okay, we want to find the Maclaurin series for our y here. To find the Maclaurin series of the y here, we need to find the dy dx and the d square y dx squared. Okay, so we already have the dy dx. From here, we just need to learn how to actually differentiate the cosecant. So differentiate cosecant gives us a negative cosecant cotangent. So we get the second derivative here, right? So we just need until the second derivative because we just need until the x squared term then. Okay, so with that, this is our y, of course. We just need to sub in the value. So when x equals to 0, so we have to evaluate all these things here. So that would be the cos of the 1 over 4 pi that we need to evaluate. So we get 2 over 2. And then for this arctan here, we just sub in, okay, into the ln form. So it's a half ln 1 plus x, 1 minus x there. And tidy up, and this is the value that we get in the exact form. So for the rest of it, okay, just sub in the 0 into the dy dx, evaluate, d square y dx square, evaluate. So after that, it will just put them back into the Maclaurin series, the formula for the Maclaurin series. So this is the value of the what is that? Yeah, the value of the y there, and then also we have got like this is like the first derivative, and then this is like the second value of the second derivative. We just put everything inside there. Okay, so that is actually what we get here, right? Okay. If you look at the next part of the question here, okay, the appropriate integrating factor, okay, for this, okay, equation, it looks very complicated. Is in fact, okay, x plus a third of x squared plus 1. Okay, so how does that like result like in this integrating factor? The first thing that we always have to do is that for this, we need to divide by the something so that the dy dx is only having the 1. So the dy dx is having like the x squared minus x squared plus 1. We need to divide the whole equation by the x squared plus 1 there. So you can see the second term here, the coefficient of the y is this one. So this actually gives us the integrating factor there. So the integrating factor here is that we have e power integrate the 1 over third of the x squared plus 1. So we can recognize this form, okay? It will give us some arc sine arc cos thingy. Refer from the MF19, okay, so it gives us an arc sine. So because we want to get the like this result here at the end, so we need to use the ln form for the arc sine. So the e and the ln will actually get cancelled off. So at last, it will actually result in something like this nice here. Okay. So this is to prove for the integrating factor. So now we need to find the solution. Okay. So the solution is we want to solve this equation earlier here. Okay. So the steps would be multiplying the integrating factor to the differential equation there. But remember always, okay, when we multiply, is to multiply to the standard form. Okay, not the original, must be the standard form. So when we multiply by the standard form, if you look at, okay, this is super complicated, right? But in fact, the left-hand side will always just become like the integrating factor times the y, or the dependent variable in this case, which is the y here. Right-hand side, okay, we might need to simplify a little bit. Okay, we might need to simplify just by a little bit. But in fact, it actually gives us quite some nice value there. Okay, so because what we could actually achieve from there is that we will actually have got something like this here when we actually try to expand it. Okay, so you can see the left hand side here, right, is like having this form. Okay, maybe we'll just look at this here. So the right hand side is actually having this form here. So we could factorize one of the x out. Okay, we could factorize one of the x out. So here we will have like x and then x minus the square root of the x squared plus 1, which could be multiplied by this x plus the square root of the x squared plus 1. So this is like a form of like a minus b. This is like a plus b. So at last, this form here is actually our a square minus b square form. So the good thing that we have here for the a square minus b square here is that the things will just cancel off nicely. It will only give us just like a negative 1 here. So that is why we actually have the right-hand side is like reduced into this kind of the relationship here. So after that is to integrate both sides. Okay, once we integrate both sides, left-hand side is having this expression here. So the right-hand side that we have here is to integrate, okay, the negative of the x over x squared plus 1. So for this, we need to recognize the form. It's like a f prime x over fx form. Okay, because when we differentiate the x squared plus 1, it should give us a 2x there. So when we actually integrate this, it means that we are trying to integrate something like this here. Okay, so that is why at last we're actually getting like a negative of the half ln of the x squared plus 1. And remember to include the constant from there. Okay, so after that, right, okay, what they actually have for us here is that we will have the x equals to 0, the y is equals to ln 2. So sub in the values. Okay, and the value of the c that we have here is actually a ln 2. So with that, it's just to tidy that up a little bit because most of the time, the question will need us to express it in the form of like a y in terms of x like that. So we just need to rearrange it a little bit. So make sure that the y is a subject here, then we can actually have this result already. Okay. Okay, so the last question that we actually have for here, okay, is that, okay, we need to use the De Mor's theorem, okay, to show that we have got like this, okay. Sine power 6 is equal to this identity here. So, okay, what we have, okay, is first we need to actually like let the z to be cos theta plus sine theta. So we know that this is actually something related to the complex number already. Okay, and the next thing that we want to start off with is that it depends, yeah. If we want to prove for the power of the cos, is we need to use the cos theta. The 2 cos theta is z plus 1 over z. But we are proving for the sine here. So we need to use a 2i sine theta is a z minus 1 over z in this case here. Okay, so for that, okay, we need to power 6 because we want to get a power 6 here. From this result, they will give us a result, yeah. We need to know from we need to able to be recall, yeah, okay, to recall this power 6 to that. So the left hand side, okay, we have got the sine power 6. 2 power 6 is a 64. And then we have got the I power 6. So the I power 6 is actually a I squared. So it's a negative 1. Okay. because every I power 4 is a 1. So when we have got I power 6, it will be just I squared. I squared is a negative 1. So it will be like become like a negative here. For the right hand side here, it's we got to use the binomial expansion, so just expand everything from there. Okay, expand. This is what we get after we actually do the expansion. Okay, we just expand there. And later on is to collect the similar powers together. And here we apply the result where z power n plus 1 over z power n is actually 2 cos n theta. So we apply this result. So this result also not even. You need to know. Okay. Sub in everything, and we can actually tidy up from there. So this is what we get for the sine power 6 there. Okay. So if you look at the next one, so given that the cos power 6 is actually like having this expression here, so we need to find the value, the exact value for this thing here. Okay, so basically it's very simple. Here, we just need to treat this 1 over 4x as a theta first. Then we simplify first because we already have the sine power 6 earlier. So now we have got the cos power 6. So they are actually quite similar, but some of the terms are negative. So that when we actually like add them together, right, it will actually be cancelled off. So this is the only expression that we have remain after we actually add the two things together. So now because they want to look for the 1 over 4x, right, so we just sub in, okay, 1 over 4x into that relationship here. So basically after we like want to integrate, right, that is just like we are integrating this 3 over 8 cos x plus 5 over 8 only. So just integrate as usual from here. Then later on is to sub in all the values from there. So we could actually get this value here. All right. Okay. So there's a bit of the question for the last part here. So express each root of the equation, okay, in the form of like a cos k pi. K is a rational number. Okay, what we have for this case is that, okay, let's see to be the cos theta first. Okay, because they say the root here is for the variable c, and then they say that c is actually having the form of like a cos k pi. Okay, so why not we just let the c to be the cos theta first, and we will see what happens from there. So basically, once we actually consider like the c is a cos theta, right? This c here is a cos power 6. So why do they actually have like a 1 minus c squared here? It is actually a sine squared. Sine squared to the power of 3 is a sine power 6 here. Okay? So after that, okay, we will actually have the result from the previous part again. So this is the cos power 6 and then the sine power 6. So this is actually coming from here, the result here. Okay, so here is the 16 of the cos power 6 plus the sine power 6 here. So we use the result that we have from this previous part here and sub in. And it actually gives us quite a nice result. So we're actually just solving for the cos 4 theta is equal to a half there. So of course here we will just have to solve the values of the 4 theta here. Okay, so for this I'm just considering the first 4 value of the theta there, because the first 4 value of the theta that we have here are not repeated. Okay, so that is where I'm actually considering like just the first 4 values of the cos here. Okay, you could just write out all the values for the theta there, and you can actually like list out all the like data here as well. But at last, we just need to look at how many roots that we need. Okay, so what do we actually need at the end here is that we are actually solving for something that is like the equation here is only having like the power 4 when we actually like look at this situation here. So what we actually need here is just like we need the 4 values of the k only. Okay, because if when you actually try to expand this one here, right, the c power 6 here will actually cancel off, and you will only have like the highest power there is c power 4. Okay, so that is why you only need like the 4 roots here at the end, right? Okay, so that will be it for this paper here.